So here's a second example of least squares curve fitting. So what we have here is what we got: the marginal cost C for taking n workers to an offshore job. It is believed that C and n have a relationship of this form. Now we might just kind of give you a feeling for what this looks like. So it's C and n is like y and x. And this is the one where n is very, very big. Well, we'll do n is small first. When n is small, an is small, so we can kind of forget about that. But when n is small, b over n, b divided by very, very small is very, very big. Now, the way to interpret that is initially, when you want to take one worker to an offshore job, that will cost a lot. Okay, then the cost will reduce. Like when you've got 5 people you're bringing already, it won't cost much more to bring one more. But what's going to happen here is, as n gets big, b divided by big number is small, so we can forget about that, but we get an, which is big, and in fact is basically a straight line, mx plus 0, essentially. So you get something like this. The idea, now I can't really explain why this model is good, it's not really good, but the idea is if it's an offshore job, you can't keep bringing more and more people. Like it actually one of this shape, but eventually it'll become a time where like you'll have to add an extra floor to the lodgings and stuff like this. But anyway, this is what we're working with. It's just a story for you to actually do the maths, give it some kind of life. Okay, so let's see what we got. Find the best values of the constants a and b in the least squares sense. Use 4 significant figures for all calculations. Now we need to look at the multipliers here. Now the first multiplier is of a, and that's quite easy. So the multiplier of a is n, and we'll form that normal equation first. So multiply everything by n and add up. So c by n and add up. So that's c by n and add up equals a by n is an squared, and add up, but take out the common factor of a. So it'll be a times add up n squared. Plus, and then b divided by n multiplied by n. So this is b divided by n. Multiplying by n is the inverse of dividing by n. So it'll undo multiplying by n. You'll just have add up the b's. Okay. The other multiplier, we can either do it as dividing by n or multiplying by 1 over n. I think you actually have to understand both. So I'll write both. So the multiplier of b, you can either think of it as dividing by n, which is the same as multiplying by 1 over n. These are the same thing. Multiplying by a half is the same as dividing by 2. So we'll use divide by n when it's easy to use, and we'll do multiply by 1 over n when that's easy to use. So c divided by n is c divided by n, and add up. Now we have a by n divided by n. So dividing by n undoes multiplying by n, you're just left with a. So it's just add up a. Now if you take out the common factor of a, like what doesn't make any sense. So you got add up a, say, it makes no sense to talk about a add up. What are you adding up? Well, it would be a by 1. And we'll get back to that in a moment. But anyway, an divided by n is a and add up. Now for the b divided by n, I'm going to use it's multiplying by 1 over n, because 1 over n by b over n, top b by 1 is b, and then n by n is n squared. So let's add up b over n squared. You want to take out the common factor of b, and so it'll be b by 1 over n squared. You might need to do some exercises to get used to that little small bit of algebra, and of course this is what you'll be recommended to do. There's going to be exercises coming up which I recommend you do. Okay, so if this was an assessment, you would have to say make a table where you find c by n and add it up, find n squared, add up, we get to that c over n and add up, and 1 over n squared. So you'd have to do some manipulation. It'll probably certainly be in Excel, but here in these questions, because they were in an exam paper, I didn't want people doing that. Excuse me, those numbers are there. So again, what I'm going to do is I'm going to write it in the form add up n squared by, I want something times a plus something times b equals something that twice, because that's easier to work with in general. So add up the n squared is 1375 times a plus add up the b's. Now here what you have to see is b is some constant. We don't know what it is. What happens if you add it up? You get b plus b plus b plus b plus b 5b. Or you could do b times add up the ones. 1 plus 1 plus 1 plus 1 plus 1. It's b times, well, adding up those 5 ones gives you 5. Whatever way you do it, this is going to be 5b. If there was an extra point, it would be 6b. Equal to add up c by n, which is 863.75. Now the other one, so add up the a's for similar story is going to be 5a plus b times add up 1 over n squared. So add up 1 over n squared is 0.059. Equal to add up c over n, which is 5.563. Now you can absolutely use Cramer's rule here, but I don't think there's any real need, because I can multiply 5 by something to get 1375a. And to find out what that is, I just do 1375 divided by 5, 275. So I could multiply this by 275. You can absolutely do Cramer's rule. In fact, I'm going to do minus 275. So minus 275 times this 5a is minus 1375a. Minus 275 by, what am I multiplying this one, sorry. So 275 by 0.059. 4 significant figures, 16.23. And it's negative. And then 5.563 by 275. And again, it's going to be negative 1530. So now I'm going to add together these two equations. So this minus this gives me 0. I have 5b minus 16.23b giving me minus 11.23b equal to, I must do 863.75 take away 1530 giving me 4 significant figures minus 693.3. And I want to get b on its own. It's multiplied by minus 11.23, so the inverse of that is dividing. So I'm going to divide both sides here of this equation by minus 11.23. That will get rid of the multiplied by minus 11.23, and I'll just be left with b. And we'll also have 693.3 divided by 11.23. I don't have to include the minuses, because minus divided by minus is plus. I end up with 61.74. Now I'm going to substitute this into this to find out what a is, and I might do it here just for space. So I end up with 1375a plus 5 times b. Now it's funny here, like you're multiplying 5 by a big number, and you can get all kind of rounding errors coming out. Ideally, it's kind of difficult. You can't be using too many decimal places, because all the measurements have errors in them anyway. So, but sometimes you might come across a situation where even a tiny difference in the rounding makes a big difference. This is going to be a theme throughout this, but for this section we can certainly just assume everything's going to work okay. So I'm going to do 5 times b. So that's 5 by 61.74. So I'm going to put in 61.74. I could have done 5 by answer. What's it coming out as? 300 to 4 significant figures, 308.8 equals 863.75. I'm trying to get a on its own. I want to get rid of this 308.8. So I'm going to take that away from both sides. And I will be left with 1375a equal to 863.75. Take away 308.8. This bit should be boring. I mean, we're just doing simultaneous equations. to four significant figures, I get 554.9, but the 9 rounds up, so I actually get 555.0. A small thing here is, obviously this number here is equal to 555, but if you want to communicate that it's actually like correct to four significant figures, you can put in the 0.0. So 555 maybe is 555.1. Whereas if you write 555.0, you know that it's equal to this to four significant figures. That's the beauty of doing that. And now I've got multiply by 1375. I don't want that there. So the inverse of multiplying by 1375 is dividing. And so I'll do that to both sides, and I end up finally 555 divided by 1375. Four significant figures, 0.43. Now here's something to look out for, these dots. If you're doing this to four significant figures, it's probably not 0.4. Like this is, you're going to get 3636. So just to be careful, 1, 2, 3. The fourth one, it's a 3. It doesn't round it up, so it would have been safe. But if it was like 6 with the dots, it would have been 6 and you should have rounded it to 0.4037. That's 63, so we'll keep it as it is. In light of what I'm saying about the rounding errors, it's kind of a bit fussy, but it's just how to round properly. Why not do things properly, I suppose, is what I'm saying. So we've got a nice model here for the marginal cost of taking n workers is given by the following model. A, which is 0.4036 times n, plus B, which is 61.74 divided by n, and sure, there's the space for it. Okay. How can we check the answer here? You could like maybe put in just some numbers and see is it roughly good, like is it in the right ballpark. So for example, if I put in n equal to 10, am I getting something? Now I shouldn't actually get 10.10 because remember it's not going to hit it exactly. It's just using the 5 points to average out because all the points have errors in them. But anyway, so 0.4036 by 10 is 4.036, and then this divided by 10 would be 6.174. So we're hoping this to come out around 10.1, 10.2. Yeah, that's good. Okay, so this is our model, and now will we see is there some questions about it? Okay. Oh, here's the thing. Using differentiation only, find the number of workers n such that C is minimized. Okay, so I suppose the thing is, if you have this kind of mental model in your head, and I think in the assessments, typically you're going to be asked to plot things. That would make things easier. But we have a minimum, no matter what, where the derivative here is equal to 0. Now we could check the second derivative as well, but it's not going to be too important. But anyway, this is what we want. We want you're going to have a minimum where the slope of the tangent, which is dc dn, is equal to 0. So what we want to do is differentiate this and find where it's equal to 0. That will give us the number of workers that minimizes the marginal cost. Okay, so I want to solve the derivative dc dn equal to 0, and we'll put this little exclamation mark that we're trying to force this. So one thing that might be useful for maybe not in this module, but how do you write I want to differentiate something, say with respect to n? You write it as d dn. So I want to differentiate this thing. Now differentiating this is no problem. This is probably a little bit more complicated. You could do a quotient rule here. It's a bit of overkill though, because you can do the divided by n is n to the minus 1. So what I'm going to do is I'm going to write this, but instead of divided by n, I'm going to write n to the minus 1. And that actually tells you as well, you could, you know, in those finding the normal equations, instead of doing multiplied by 1 over n or divided by n, you could do multiplied by n to the minus 1. That would be an option. So let's put in c here, 0.4036 n plus 61.74 divided by n is n to the minus 1. I don't seem to be giving myself enough space here, so I'm going to have to do a bit better. Okay, so this means differentiate c with respect to n and get 0. Off we go. So again, I'm going to recommend fixed constant differentiate. So fixing the constant, I get 0.4036 0.036. The derivative of n with respect to n is 1. Fix the 61.74. And how about the derivative of n to the minus 1 is multiply by the power, reduce the power by 1, so it goes from minus 1 down to minus 2, equal to 0. Now I really don't have much space here for solving this, which isn't ideal. What are we going to do? Okay, what we're going to do is as follows. We're trying to get n on its own. So the first thing we want to do is maybe get rid of this 0.4036 by 1, which is just 0.4036. So we're going to take away 0.4036 from both sides, and so we'll get, and then we're going to do something concurrently. So I've 61.74 by minus, that's minus 61.74. And n to the minus 2 means divided by n twice. You want to use the negative powers when you're doing some kind of manipulations and differentiating, but if you're hoping to solve equations and stuff, you go back to the negative power being 1 over n squared, negative power being division. That's actually something, I don't know, is it pushed enough? So if you do n by n by n, that's n to the 3, but divide by n 3 times, that's n to the minus 3. So anyway, this is divided by n twice, that's divided by n squared. So where are we now with this problem? So it's a messy little equation. What I would say to you here is you shouldn't like this n squared down here. You don't want that. It makes things difficult. So what you need to do here is you've got division by n squared. You don't want that. What's the opposite of division by n squared? Well, I'll get rid of that n squared. Multiply by n squared. I'm also going to multiply by minus at the same time to get rid of these. So I'm going to multiply by minus n squared. So the minus by the minus is plus. That's sorted. And I've got divided by n squared multiplied by n squared. That's going to undo the division by n squared. I'm just going to have 61.74. The minus taking care of that. 61.74 equal to, and now the minus by the minus is plus 0.4036 times n squared. Now the other thing, and I have very little space here, is, so I've got this little equation. If this is equal to this is equal to this. So if I want to get the n on the left hand side, I can do it. That's no problem. I want to get n on its own. I got this multiplied by 0.4036. I want to get that out of there, so I'm going to divide again by 0.4036. Well, I'm going to divide by that, and I'm going to have this equal to this. So n squared multiplied by this divided by it is just n squared, equal to 61.74 divided by 0.4036, giving me four significant figures, 152.99, which rounds it to 153.0. And now, how do I get rid of the square? The inverse of squaring is square rooting, but I have to be careful here because there's actually two solutions. We'll do the square root and we'll worry about the two solutions. So I'm going to do the square root of both sides. The square root is going to kind of get rid of the square. And I'm just going to do the square root of 153 here. And I get to four significant figures. 12, I'm getting a slightly different answer to what's going on here, but that's okay. We'll talk about that. Okay, so what's going on here, right? So we're trying to find where this minimum is. We found this thing here. I said there's two solutions. So if you square 12.37, you get this 153, but there's actually two numbers that square. Minus this will work as well. So when you're taking a square root, you want to know that, well, here, that there's two solutions, plus or minus. And then you think about the problem. This problem, you're talking about numbers of people, and you can't have minus 12.37 workers. So throw out the minus. So you're getting an answer here of 12.37. Now this is supposed to be the number of workers, but you can't have 12.37 workers. So what you have to realize is, if you think about the graph, the minimum is happening at 12.37, So the answer for us, because n is only a whole number, is either 12 or 13. So I think what we have to do is we have to go back to our model and substitute 12 in and 13 and see which one gives us the smaller value. So if I substitute 12 into my model, 0.4036 by 12 plus 61.74 divided by 12, this one gives me 9. I'm just going to do 3 significant figures, 99, and now I'm going to throw in 13. It actually rounds to exactly 10. It's 3 significant figures. So this one is bigger than this one, so the answer is actually 12. Answer n equal to 12. Now, you can talk about the second derivative here, and you could actually just check. If you differentiate this a second time, this will go to 0. This is negative at the moment, but if you differentiate it again, you'll have the minus by minus 2, which would be plus 2 by this, and you'll have n to the minus 3. The second derivative is something like let me see, 100, well, it's 61.74 times 2 by n to the minus 3, which is divided by n 3 times. And that's always positive. Now what that means, it always has the smiley face, as you see here. So it's certainly a minimum, but really in these questions it's going to be obvious that there's a minimum. Now maybe it's not obvious from the data that it starts expensive, gets a minimum, and then gets more expensive. Now the question mark here is, what am I going on about 11 and 12? So when I did this question here, I've done it in front of us. I don't think I actually have made a mistake. I'd be interested in anybody checking my answers, but my suspicion is that there actually has been some rounding error somewhere. So if I found, for example, here we found B first. If we found A first, you get slightly different answers, and they can make a big enough difference. Like here, dividing by a small number, or if we use more significant figures, maybe the answer came out a little bit different. You're certainly kind of suggesting that, I mean, it's near 12, so maybe the rounding pushes it to, I don't know, 11.9, and if I remember correctly, that's what it actually gives you. But we have to work within the confines of the rounding error here. Okay.